In this lesson, we look at how negative numbers can be represented in binary. We will introduce 1's complement, see how negative values are formed, and explain why addition requires a special end-around carry in 1's complement. Computers store numbers as fixed sequences of bits. For example, with 8 bits, the positive number 53 can be written as 0, 0, 1, 1, 0, 1, 0, 1. The difficulty in representing the negative number 53 lies in that the bits themselves do not include a minus sign. So we need a rule that allows some bit patterns to represent positive values and others to represent negative values. One approach is called 1's complement. In 1's complement, we represent a negative number by flipping every bit in the positive representation. A 0 becomes a 1 and a 1 becomes a 0. Let's represent negative 53 using 8 bits. The positive value 53 is 0, 0, 1, 1, 0, 1, 0, 1. Now flip every bit. 0, 0, 1, 1, 0, 1, 0, 1 becomes 1, 1, 0, 0, 1, 0, 1, 0. So, in an 8-bit 1's complement system, 0, 0, 1, 1, 0, 1, 0, 1 represents positive 53, while 1, 1, 0, 0, 1, 0, 1, 0 represents negative 53. The leftmost bit can help us identify the sign. A leftmost bit of 0 indicates a non-negative value, while a leftmost bit of 1 indicates a negative value. However, the remaining bits should not simply be read as the magnitude of the negative number. To determine the magnitude of a negative 1's complement number, we flip all of its bits again. For example, suppose we are given 1, 1, 1, 0, 0, 1, 0, 0. Since the leftmost bit is 1, this represents a negative number. Flip all the bits. 1, 1, 1, 0, 0, 1, 0, 0 becomes 0, 0, 0, 1, 1, 0, 1, 1. The binary value 0, 0, 0, 1, 1, 0, 1, 1 represents 27. So, 1, 1, 1, 0, 0, 1, 0, 0 represents negative 27 in 1's complement. Flipping the bits creates a direct relationship between positive and negative values. Every positive bit pattern has a corresponding negative pattern obtained by inversion. Now let's look at addition. Suppose we want to calculate 42 plus negative 19 using 8-bit 1's complement. First, represent positive 42. 42 is equal to 0, 0, 1, 0, 1, 0, 1, 0. Now represent negative 19. Positive 19 is 0, 0, 0, 1, 0, 0, 1, 1. So we flip all the bits. 1, 1, 1, 0, 1, 1, 0, 0. And the calculation becomes 0, 0, 1, 0, 1, 0, 1, 0 plus 1, 1, 1, 0, 1, 1, 0, 0, which equals to 1, 0, 0, 0, 1, 0, 1, 1, 0. The addition has produced a 9th bit to the left. Since we are working with an 8-bit representation, this extra bit is a carry out of the most significant bit. The most significant bit, or MSB, is the leftmost bit. In 1's complement, this carry is added back into the rightmost bit. This is called an end around carry. Remove the carry from the left, leaving 0, 0, 0, 1, 0, 1, 1, 0. Then add the carry to the result. 0, 0, 0, 1, 0, 1, 1, 0 plus 0, 0, 0, 0, 0, 0, 0, 1, which becomes 0, 0, 0, 1, 0, 1, 1, 1. So the result is 0, 0, 0, 1, 0, 1, 1, 1, which represents 23. This agrees with the decimal calculation. 42 plus negative 19 is equal to positive 23. The end around carry is needed because the arithmetic takes place within a fixed number of bits. When the addition produces a carry beyond the leftmost bit, that carry still contributes to the result, so it is wrapped around and added back on the right. 1's complement has an important problem. Consider positive 0 in 8 bits. That is 0, 0, 0, 0, 0, 0, 0, 0. If we flip every bit to produce its negative representation, we get 1, 1, 1, 1, 1, 1, 1, 1. So 1's complement has two representations for 0. A positive 0 and a negative 0. These patterns represent the same quantity, but they are stored differently. This makes comparisons and arithmetic more complicated. The intuition behind 1's complement is that a fixed collection of bits must represent both negative and positive values. One group of patterns represents non-negative values, and the inverted versions of those patterns represent the corresponding negative values. This gives a simple rule for changing the sign, but the duplicate 0 and end around carry make the system less convenient.